Okay, this is the midterm review packet. So we're going to cover topics in the first 5 units, which includes measurement, vectors and scalars, motion in one dimension, motion in 2 dimensions, forces, momentum, and impulse. This covers about 40% of the physics curriculum for the year, even though we are at the halfway point. So let's go through one by one. I'm going to try to move quickly. The thickness of one page of the test booklet is closest to, well, let's see, definitely not a meter, definitely not 100 meters. That's 1 centimeter. That's still way too thick. It's got to be this. That's 1/10 of 1 millimeter, so less than a millimeter. The maximum time allowed for the completion of this exam is approximately, oh my gosh, we got to do a little math here. 3 hours, right? Because your average Regents exam is 3 hours. You use another number like 1 hour, you're still going to get close enough. 3 hours times 60 minutes in an hour and 60 seconds in a minute gets us 10800 seconds. That's roughly 10 to the 4th. Answer C. Which object weighs about 1 Newton? 1 Newton would be like a small cell phone or a small apple. Probably in this case, a golf ball is 1 Newton. That is the weight. If you see a 1 Newton object, that means it's its weight. What's a derived unit? It's got to be a Newton. Newton's kilogram, meter per second squared. And in case you're not sure, you can also look at force equals ma, mass times acceleration, kilograms times meters per second squared. Which combination of fundamental units can be used to express the weight of an object? Weight is a Newton, right? Weight's a force of gravity. So as I just did, kilogram meters per second squared. Answer D. Circular motion, a roller coaster starts from rest and accelerates down a track, blah, blah, blah. Which diagram best represents the path followed by an object that falls off the cart at point D? So at point D, remember the velocity is tangent, so that would be your velocity there. Should be straight down. Answer A. Centripetal force F sub c is acting on a satellite. The speed is equal to, so F sub c equals, you'll see it's equal to mc, ma sub c, but it's also, if you look up a, mv squared over r. So we're just going to solve for v because its velocity and speed are often treated the same. Not always exactly the same, but so that means if F equals mv squared over r, and we want to solve for v, fr is going to equal mv squared, divide both by m. Fr equals v squared, so the square root of that is going to be equal to v. Right there, fr over m. Answer A. That's the page. Okay. Number 8. Advance your answers on the blah, 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 stuff. What is the speed of the cart? I bet you we don't even need to read that. It's a 2 kilogram cart, 3 meter track. I take it back. We do need to actually read that because we need to get the centripetal force right here is 24 newtons. So if 24 newtons is mv squared over r, 24 equals 2 kilograms. V squared over 3 meters. So 24 times 3 divided by 2. Take the square root of that, and we should get 24 times 3 divided by 2 is 36. Square root of that is going to be 6 meters per second. Okay, circular motion. At the instant shown in the diagram, the car's centripetal acceleration is. So we didn't even need to read any of this to answer this question. The centripetal acceleration is towards the center of the circle. That's right here. That means it is heading east based on this northeast, southwest. Okay. A ball attached to a string is whirled at a constant speed. So even though it's constant speed, we know that there is a net force and acceleration towards the center of the circle because it is centripetal motion. What's the magnitude of the centripetal acceleration? Magnitude is going to be v squared over r. V squared over r. So velocity is 2 meters per second over a radius of 0.5. So 2 squared is 4. Divided by a half, that's doubling that again, that's 8. So 8 meters per second squared. What is the best description of the force keeping the ball in the circular path? Well, you know it's got to be inward. Strings can't push outward, and circular motion always has an inward force. So the force is perpendicular to the circle and directed towards the center of the circle. That sounds pretty good. Perpendicular circle and directed away. That's not true. It's definitely not directed away, and it's not tangent to the circle. Tangent to the circle and directed in the same direction. The ball is moving. That would be the velocity. This is the force. Same direction as the acceleration. The force is always in the same direction as the acceleration for net force. The magnitude of the force applied to the string by the student's hand is increased. The magnitude of the acceleration of the ball in the circular path will, okay, F equals ma. So if you increase the force, you increase the left side of the equation, you got to increase the right side of the equation. So if you increase the force, then your acceleration should increase also. Let's look at some projectiles. Lots of da-da-da-da-da. Okay, let's just read the question. The total horizontal distance traveled by the tennis ball during the entire time in the air is approximately. So we know that it's going, we want to find the horizontal distance, so we're going to deal horizontally. And if we're dealing horizontally, it's constant speed, so we can just say distance is velocity times time. And the velocity, it is kind enough to give us, we don't even have to calculate it, it's already got the components, is 9 meters per second is the horizontal velocity right there, which is the same as the vertical velocity, but we're dealing horizontally. So now we just need the time for the trip. So the last thing we know is that it takes a 0.92 seconds to reach the top. So when it hits here, it's going to take 2 times 0.92. So that's 1.84 seconds. So 9 times 1.84 seconds gets us times 1. I bet you I don't even need to do this. 16.56. That's going to round up to 17 meters. So yeah, I bet I could have done that without even just looking at those, because I knew it had to be bigger than 9, but definitely less than 18, and that would have eliminated every other answer. So no calculator even needed. Sometimes the speed at which the launcher fires a tennis ball is constant, but the angle between the launcher and the horizon can be varied. As it goes from 45 to 30, the range should decrease. 45 is maximum range, so getting away from that will cause you to decrease the range. So, okay, decreases. The path of projectile can be described as parabolic, because they are all parabolic paths with projectiles. Projectiles launched with an initial velocity of 200 meters per second, angle 30 degrees. What's the magnitude of the vertical component? So 200, and that would be 30 degrees meters per second. So the vertical component we are looking for is this, right? V sub y. So that would be 200 sine 30. And it's sine because we're looking at the opposite. Sine 30 should be a half. So 200 times 1/2 should be, oh, it even gives us, okay. We don't even have to do the math. 200 sine 30. Answer B. Okay, if the ball's time of flight is 10 seconds, what is the vertical component of the initial velocity? Well, you could do this with kinematics. The nice thing is it's giving you a 35-degree angle, but you can actually completely ignore that because all you care about is the vertical component. So we don't care about the horizontal component, and we don't know a range, so we can't work from there anyway. So the easy way to think about this is every second it loses 10. So in order for it to be in the air for 10 seconds, it's got to start at about 98 meters. Sorry. It's got about half of 98 meters. I'm going to pause this for a second. Okay, so it's going to start with the velocity and with the negative of the velocity. So in order to be in the air for 10 seconds, it's actually, I can tell you this, it should have 49 meters a second because it's going to be 49, 39, 29 roughly, 19, 9, 0, negative 9, negative 19, negative 29, negative 39, negative 49, because it starts with an initial and ends with a final that is opposite to that. But you can calculate this. You could just say d vi, vf, at, and set these to a couple different variables. Negative 9.8 time is going to be 10 seconds. Now you do not know the distance or VI or VF, but you know that whatever this is, let's call it VI, VF is negative VI. So interestingly enough, if you just put it into the equation, VF equals VI plus AT, you'll end up getting negative VI equals VI plus AT. And so we can actually solve this only knowing two variables, because you get negative 2 VI equals AT, where A is 9.8 meters per second squared, and we're going to put a negative on that. Time is 10, so 9.8 times 10 is 98, divided by 2 is 49, gets us the answer there. Another way to do it, if you want, is you could say, oh, I only know, instead of getting just two variables, you could just do half the time, and you could say, what is the initial velocity if the final velocity is 0? And it takes instead 5 seconds to get there. And then solve for it again. VF 0 equals VI plus AT, negative 9.8 meters per second squared, times your time of 5. Solve for that, and you get VI is equal to 49. Three different ways to get that same problem. So need to rewind that one, see it again, feel free. If the angle of elevation of the cannon is decreased from 35 to 30, the vertical component will. So as you lower the angle, the vertical component should go down. So it will decrease. But as you get more horizontal, the horizontal component should increase. So answer B. Lower angle, decreased vertical, more horizontal. If a ball lands from the cannon 10 seconds after it was fired, what's the horizontal component of the initial velocity? Note, this still goes with this question, because that could be important if we need to know the angle. So it lands 10 seconds. What's the horizontal? Okay, so we're dealing horizontally. And fortunately, we don't even need the picture. We don't need the angle. Because horizontally, we know it's going at constant speed, so D equals VT. The velocity we don't know, but we know the distance is 7 times 10 to the second. That's 700 meters equals your velocity, which is our variable, times the time of 10 seconds. So V is 700 divided by 10, 70. Answer A. Okay, a projectile is launched at an angle of 60 degrees above the horizon. Like lots of stuff. Okay, that's probably all described in the picture right here. What's the magnitude of the vertical component of the projectile's initial speed? So there's more than we possibly even need to know. It's got an initial speed of 40 meters a second and an angle of 60. So 40 meters per second, angle 60 degrees. So the vertical component, which is this side right there, is going to be 40 times the sine of 60 in meters per second. So you can put that into your calculator. You can do 40 times sine of 60, which, oh my gosh, weird calculator, 0.866. Oh, that's the sine of 60, there we go. Times 40, should be about 35 meters per second. I'm going to pause this while I get a different calculator. Okay, so I got a new calculator. The value of a good calculator cannot be underestimated. You'll notice this has sine, cosine, tangent buttons right there. Make sure you take a test with a calculator you are comfortable with, because if you're not, then you're going to struggle. If you try to use cell phones in general, the calculators suck. That's why I really suggest a decent scientific calculator. Okay, which graph best represents the horizontal speed of a projectile as a function of time? So let's think about this. Projectile's horizontal speed. Horizontal should be constant speed because it does not change. There's no acceleration. Gravity does not pull horizontally. Gravity only pulls down. So horizontal speed constant, answer D. Okay, projectile off a cliff. Which diagram represents the position of the ball at 1 second intervals? Okay, so we know it's going to follow a parabolic path of some sort, and that horizontally it should be evenly spaced, but vertically it's going to get bigger and bigger and bigger and bigger. So this one right there, you'll notice that horizontally they're all about the same distance. But vertically it gets bigger, small, bigger, bigger. Answer D. 2 kilogram block is dropped off the roof of a tall building. Which statement describes the motion of the block and the motion of the ball? So the block is dropped off the roof and a ball is dropped off the roof horizontally. So one is dropped and one is thrown horizontally. They have different masses. One's a block, one's a ball. Interestingly enough, if you ignore air resistance, they should both fall at the same rate. They both start, kind of like this question, they start with 0 initial vertical velocity, so they should hit the ground at the same time. This is a horizontal launch. Our initial vertical velocity is 0, so I like this because it's round. They have ones where it's like, it's red, it should hit the ground first. They hit the ground at the same time. They have the same vertical acceleration. That is 9.8 meters per second squared. All projectiles and falling objects have a vertical acceleration of 9.8 meters per second squared, which means that they have a total acceleration of 9.8 meters per second squared, because horizontally it's 0. Smokestack. Okay, snowballs released. The horizontal component of the velocity is, let's see, it travels 15 meters, and it takes 0.65 seconds to do it. So if D equals VT, D equals VT, T is going to equal D over V, distance over velocity, 15 meters per second, divided by, I'm solving velocity, sorry. V equals D over T, 15 meters per second, divided by the time of 0.65 seconds. And we can do this because horizontally it's going at a constant speed. There's no horizontal acceleration. Divided by 0.65. 23 meters per second. There we go. Baseball player throws a ball horizontally, which describes the ball's motion after it's thrown. Neglect air resistance. Okay. Vertical speed remains the same. No. Vertical speed remains the same. No. Vertically it should speed up. It's thrown horizontally, so vertically it starts with an initial speed of 0 and then gets faster and faster and faster in the downward direction. So vertical speed increases. There we go. Horizontal speed is what stays constant. Remains the same. Okay, what represents a vector and its representative unit? Oh, vectors. We need to know which are which. Weight is a vector. Weight is the force of gravity. Forces are measured in newtons, so that is not the right answer. Mass is not a vector, even though it is measured in kilograms. It's the amount of matter. An amount of something is not going to be have a direction associated with it. Force. Well, we said force was measured in newtons, just like weight was the force of gravity, so that looks like the right answer. Momentum is a vector quantity, but it is not measured in newtons. It is measured in kilogram meters per second, although you could do newtons times seconds as well if you wanted to, just like impulse. Same kind of question. Which are both scalar quantities, so no direction. Well, displacement has a direction, velocity has a direction. Distance does not have a direction, nor does speed. Displacement has a direction, speed does not. Distance, velocity does not. Okay, so it's got to be answer B, distance and speed. Block on a horizontal surface, 100 Newton force acts on the block at an angle. What is the magnitude of the force if it establishes equilibrium? Okay, so to establish equilibrium in this case, we're not going to deal vertically. Vertically, you have a few things going down. You got gravity, you've got a normal force, and you've also got an upward component of this. In theory, they should all balance out. Because it's moving on a flat surface, it has to be balanced vertically because it's not leaving the surface. It does not have to be balanced necessarily horizontally, although this case says it does. So if it does, that means a backwards force, F, is got to be equal and opposite to a component of that forward force. And that horizontal component is adjacent to that side. So that F is going to equal 100 newtons times this cosine of 30. Cosine 30, which you could probably know for now, 0.866, right, times 100 gets you 86.6, answer B. Remember, this is balanced with that because we are establishing equilibrium. Two students are pushing a car. What angle should the student's arms use to maximize the horizontal component of the force? So if you want to maximize the component, you want to be pushing directly in that direction. And this is a weird question, but what you'd want is the lowest angle possible because angles are measured from the horizon usually. So you want theta there to be as small as possible. And in this case, the smallest angle is going to be 0. So just push it at 0 and you're pushing straight horizontally. How many components can a single force be resolved? An unlimited number. Although often what we will do is we'll take a force and resolve it into just 2, an x and a y. You can do any number. They don't have to line up in the x and y direction. The vector represents the resultant of two forces acting concurrently, meaning acting at the same time on an object at point P. Which vector represents two concurrent forces that produce this resultant force vector? So basically, what two forces can we add together to do this? Now, an easy answer would be one to the left and one up. So you could go left and up, and that makes your resultant R. However, that is not a choice. There's a left and a down. There's an up and a right. Neither of those work. So let's instead complete the parallelograms. So if this had a resultant, that resultant would look like that, up and to the right. That's not what it is. If we complete the resultant here, left and down, that would be your resultant there. Down to the left, that's not your answer either. We're starting at point P. So let's see if we go up there. The resultant for this one's going to go a little bit, mostly up, a little bit to the right. That's not the right answer. However, this one, start at the beginning and at the end, boom. From there up to the upper left, so it's going to be answer D. Okay. The diagram shows a kid following a sleigh. The vertical component is approximately. So in this case, the mass of the kid doesn't matter. We can ignore that. It's just going to be this, no wait, sorry, this is the vertical component, which is going to be opposite your 40-degree angle. So it's going to be 300 newtons times the sine of 40. And I could probably make a pretty good guess about what it is, but let's just do 300 times sine 40, close parentheses, and 192 is approximately 190. The diagram below shows a person exerting 300 newtons of force on a handle. The component that acts perpendicular to the ground, so perpendicular is this way, right, is approximately, so if that's 300 newtons and that's your angle, 60 degrees, this side is opposite that angle, so it will be 300 sine 60. So we can put that in, times sine 60. 259, so approximately 260 newtons. Okay, a block at rest on a ramp makes an angle if the angle increases. Let's think about it. Is the mass going to change? Definitely not. Is the weight going to change? Definitely not. The weight is just mg, and so if the mass doesn't change, the weight's not going to change unless you go to like a different planet or something. The block's component of the weight parallel to the ramp will decrease. So it's got to be one of these two, right? And the weight parallel to the ramp is going to be, if that is your weight right there, there's a component that goes down the ramp that looks a little bit like this, right? And that's your angle theta. So this, and I wish this was on the reference table, it's not. The component down the ramp is equal to mg, the object's weight, times the sine of the angle. So if the angle gets bigger, the component down the ramp should get bigger. So component parallel to the ramp will increase. Because down the ramp is parallel to the ramp, it's just saying the net force is going to point down there. Gravity doesn't point down there, gravity points straight down. But if you look at the components of gravity, you see that some of those components carry it down the ramp. And that makes sense because the bigger the angle, the more force you should have carrying it down the ramp, the faster it accelerates. And more acceleration tells you that there's more force. 200 Newton force and 150 Newton force simultaneously on a crate. Okay, which diagram basically gives the biggest acceleration? So 100 Newton, 150 and 200 Newtons. Well, think about it this way. If you have 200 to the right and 150 to the left, your net force is going to be 50 to the right. If you have 200 in that direction and then a 150 down, you can find the net force by finding the resultant, which is the square root of 200 squared plus 150 squared. Now, I'm not going to calculate that. You can if you want to. We could figure it out. Honestly, though, this is going to have the same net force because it's another right triangle with sides of 150 and 200. However, answer A is going to be the correct one because if you think about it, 150 to the right and 200 to the right, they're both to the right. They just add together, so you get a net force of 350 newtons to the right. Okay. A student walks 40 meters along a hallway that leads due north and then turns and walks another 30 meters due east. So you go 40, then you go 30 due east. What is the magnitude of the student's displacement? So that's the resultant of this. How far from the beginning did he get? 30, 40. Well, you can do this in your calculator. R is going to be the square root of 30 squared plus 40 squared. I'm pretty sure that's going to be 50 because we're doing right plus 40 squared, so it's the square root of 2500. So let's take the square root of that. 50, right? Pretty sure that is because that's basically your 3, 4, 5 triangle right there, 30, 40, 50. Which concurrent forces could result in having a magnitude of 10 newtons? So these always throw students, but think of it this way. If you had 4.7 newtons and 5 newtons, right? At most, if they're in the same direction, they could add up to 9.7. At least, if one went in one direction, the other was in exactly the opposite direction, they could be 0.3 newtons. So the resultant can be any place between 0.3 and 9.7, not 10. Here, 10 and 30, at most, it could be, add them together, 40. At least, it could be 30 in one direction, 10 in the opposite, so that's going to give you 20. So that's 20 to 40. That's not going to be in the right range. Here, a 4.7 to 4.7, at most they could give you 9.4, and at least they could give you 0, so anywhere between there. And this, 10 and 10, when it might not seem like it, can be anywhere between the difference and the sum, 0 to 20, so the answer is going to be A. It's the only one that falls in that 10 range. And if you're not sure how to get it, just imagine forces that formed an equilateral triangle like that. Sort of like that. It's not the best drawing. Okay. The equilibrium of F1 and F2 is, so the equilibrium establishes equilibrium. So if this is your resultant from beginning to end, your equilibrium goes back to the beginning. It gives you basically your resultant of all these three of A, B, and C would be 0. So if you go this way, you go that way, you go this way. As forces, the total should be 0. So 10 and 10. You know it's got to go southwest. Now there's two of them that go, so say southwest. So let's think about that. The resultant is going to have sides of 10 and 10. And it's the hypotenuse. So r squared is 10 squared plus 10 squared. So r has got to be the square root of 200. You do that, you should get 14. But you can also just look and say, hey, there's no way if that side's 10 and that side's 10 that side's 20. You just can't, you can't get a side that is that big. Okay, which ones could not produce equilibrium? So you need to get not back to 0 So if you look at it, let's think about this. This one's a little bit weird, but if you go 5 in one direction and then you start walking backwards, and I know these are newtons and so forces, but not displacements, but you can treat them kind of similarly. If you have a force of 5 newtons to the right and you have a force of 3 newtons to the left and another 1 newton, the problem is that you've started with 5 and you've only gone back 4. You cannot reach your starting point again. With any other one, you can do this. And in fact, one way to look at this is, can you create a triangle that has these sides, 3, 4, and 5? Yes. Can you have a triangle that has 2, 2, and 2? Yes. Can you have a triangle that has 4, 4, and 5? Yes. Because those triangles, those sides could represent the different sides of your components and your resultant. Which vector best represents the resultant of these two forces? Lots of stuff here we can ignore. It's got to be down to the right, so it definitely can't be A or C. And if you want to know how big it is, you've gone 30, 40, so your resultant, so this is another 3, 4, 5 triangle, should be 50. Remember, vectors, you need to add them using trigonometry. You can't just say 30 plus 40 equals 70. That's not the case with vectors. Okay. Which diagram represents the resultant of these two forces? Let's see, you go 6 and you go 10. So the resultant is going to be up to the right. Should be D. There we go. I'm going to probably stop somewhat soon. This has been a long video. Parachutist. It's got a drag force up and a weight down. As a result of the forces, the parachutist may be moving. Let's see, does it say any more? The upward force is equal in magnitude but opposite in direction to the force, the weight of the parachutist and equipment. So basically it's saying this is balanced, aka your net force is 0. So if your net force is 0, you're not accelerating. So, and your speed is not changing. So if it says decreasing speed, that's not correct. If it's saying decreasing speed, it's not correct. It says upwards with constant acceleration. Well, if net force is 0, acceleration is 0, right? So, no. It's got to be downward at constant speed. Now, just to point out, this could be moving upward at a constant speed if the drag force was caused by an updraft. So you don't necessarily know. It could be moving sideways. There's different ways in which something can have balanced forces. Which vector represents the frictional force acting on the block? It's sliding down the incline. Friction will be up the incline. Answer B. A 50 Newton force is needed to keep an object weighing 100 newtons moving at a constant velocity. Blah, blah, blah. You don't probably even need to know the velocity across a horizontal surface. The frictional force acting on the object. So it's constant velocity. That means it's balanced. That means your net force is 0. That's very important, because that means if you're applying 50 newtons of force and there's a frictional force back, it's also 50 newtons. The 500 newtons, like that might be the object's weight, and that would be the normal force also. But the frictional force has got to equal the applied force in this case. Okay. A student applies force to slide a piece of wood at a constant speed. We're going to always look for that sort of language. The wood's cut in half and changes orientation. What's the force of required to slide the wood at a constant speed across the surface? So, interestingly enough, if you look at the friction equation, mu times F sub n, the normal force isn't going to change because the object has the same weight, and in this case, the weight is equal and opposite to the normal force. The coefficient isn't going to change. You still have wood on a whatever surface that is. So according to this equation, the shape shouldn't matter at all. So if it took 10 newtons in this orientation, it should also take 10 newtons in this orientation. A book weighing 20 newtons slides at a constant velocity down the ramp. Constant velocity, ding, 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 30 degrees. What is the force of friction? Okay, as I was saying, you got a book. It's got a weight of 20 newtons. That means the force of gravity downwards is 20 newtons, going at a constant velocity. What is the force of friction between the book and the ramp? Oh, interesting. A little bit challenging. Let's just think of it this way. That weight, that 20 newtons pulling down on it, some of it has a component down the incline. And that part down the incline is equal to the weight, 20 newtons, times the sine of the angle, sine 30. 20 times sine 30 is 10 newtons. So if the force down the incline is 10 newtons, or at least a component of the weight that's carrying it down the incline is 10 newtons, well, if it's moving at a constant speed, then the frictional force has to be equal and opposite to that. So it's got to be 10 newtons, and it's got to be up the ramp. I would bet you 20 cosine 30 is 17. And that 17 is going to be your normal force. That is a component that is perpendicular, that's going to be equal and opposite. And if you're not sure which is which, think about it this way. It is a small angle. 30 degrees is not a big angle. So you would expect the force down the incline, 10 newtons, to be smaller than the perpendicular force, 17 newtons. If it was a 60-degree angle, these numbers would be switched. So a small angle should have a smaller force. A bigger angle should have a bigger force. Down the incline then is perpendicular. Okay, 47. With surface B, blah, 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 same texture as surface A, but twice the surface area. So what we found from this question up here is that the orientation didn't matter, doesn't matter which side you turn it on. So force F is required to slide the block at a constant speed across the table. What force is required? It should be the same force. It should also be force F. And I'm going to stop here because we're getting into weight and gravity, and we can continue this in another video.